Swayam Prabha. Digital India. Educated India.
So let's talk about rheology of fermentation fluids. Now fluids are classified depending on their fluid behavior into either Newtonian types or non-Newtonian type of fluids. Generally most of the fermentation broths, these are aqueous solutions, and because they are homogeneous, so we assume that they continue to behave as Newtonian fluids till the end of the fermentation. However, depending on the production platforms which we use, like plant cells or tissue cultures, which tend to aggregate, which with high cell densities may not be homogeneous, and therefore they tend to deviate from the Newtonian assumption and they behave like non-Newtonian fluids. So let's just revise what we earlier have known about the Newtonian and non-Newtonian fluid behavior. So now for Newtonian fluids, we know they follow Newton's law of viscosity, where the viscosity is said to be a function of shear stress to shear strain. Now this proportionality constant of shear stress versus shear strain plot is what we know as absolute viscosity. So any deformation which might happen in a fluid will be due to the stress which will be imposed on it. So Newtonian fluids, they follow Newton's law, and shear stress is linearly related to the rate of shear strain, and viscosity, to define, of a fluid measures its resistance to flow under the applied shear stress. So some examples of the Newtonian fluids are like water, oil, gasoline, alcohol, kerosene, benzene and glycerine. Now what are non-Newtonian fluids? Non-Newtonian fluids can further be differentiated into different forms, like pseudoplastic, where example is blood plasma, or syrups which we drink, or ink. Fermentation fluids come under this class. Now dilatant behavior, it's like starch in water, or Bingham plastic is like mustard or toothpaste. Now there are another kind of, so these all come under time dependent independent fluids, which means their viscosity is time independent. But there are certain non-Newtonian fluids whose viscosity is time dependent. These can be further classed into being rheopectic or thixotrophic. So fluids which do not obey Newton's law, which is nothing but shear stress is not linearly related to the shear rate, then the viscosity, which is mu, is no more constant and it depends on the shear rate. Now this is called as apparent viscosity. So the examples, as I said, the Bingham plastic. Shear thinning liquids is what is pseudoplastic, where fermentation fluids are classed, and shear thickening is dilatant fluids. So the impeller, if you remember, it helps in creating more shear and also therefore in reducing the viscosity. Now in general case, we know that viscosity is equal to shear stress to shear strain. In non-Newtonian fluids, your viscosity, which is called as apparent viscosity, is then dependent on the shear strain as well. So if you see the plot on the slide, you can clearly see the inclined straight line in the center passing through the origin. This shows a Newtonian fluid behavior, where the plot is between the shear stress and shear strain. Shear thinning are your dilatant fluids, shear thinning are your pseudo plastic fluids, and shear thickening are your dilatant fluids. So, in order to understand what does shear thinning or thickening means, if you make a plot of viscosity versus the applied force, which is your shear stress, you can find that in shear thinning liquids, the viscosity will go down as the stress keeps on increasing. Similarly, in shear thickening, the viscosity will keep on increasing as the shear stress is increased. Whereas for Newtonian fluids, in the same plot of viscosity versus stress, the viscosity would be a straight line parallel to the x-axis, which is the shear stress. So, your power law model is used to define the non-Newtonian fluids. So, power law index as shown on the slide is defined as N, which is a measure of a non-Newtonianness of a fluid, and if that N becomes 1, then this is the Newtonian fluid. So, for shear thinning fluid which are pseudoplastic, it is between 0 and 1, and for shear thickening fluid which are called as dilatant fluids, the N value becomes greater than 1. Your K is called as proportionality constant, which is called as consistency index. It is the viscosity at a shear rate of 1 second inverse. If you see time dependent behavior in a plot of viscosity versus time, you can see that, so apart from shear dependency, there are some fluids which also exhibit reversible time dependent properties. The viscosity, for example, of a thixotropic fluid, it decreases with time and implies a progressive breakdown of structure. So, you can think of an example where with time there is a progressive breakdown of the structure of the molecules in the fluid which cause the viscosity to reduce. The opposite of this is a behavior which is observed in thixotrophic fluids, where it becomes like a, with time it becomes thicker and thicker. Can you think of an example? So, if you make a plot between viscosity versus time, so then you can see on the plot, once the shear is stopped, then for eupectic fluids, the viscosity increases with time, and for thixotrophic fluids, the viscosity will decrease with time. And the in-between line, which is parallel to time, which means that viscosity is constant. It is not dependent on time. So, these are time independent fluids. So, where do fermentation fluids lie? Bacterial fermentation fluids, they behave like Newtonian fluids because they can be assumed as very homogeneous, uniformly suspended single cells. But its viscosity may change if the cell concentration increases and it becomes a very high cell density process, like in case of perfusion reactors, continuous reactors with cell recycle. So, there with time you may observe that the behavior may deviate from Newtonian fluid to a non-Newtonian fluid. So, the change which you will observe may not be a linear change. Another example is fungal fermentation medium, which behaves like pseudoplastic fluids, which are called as shear thinning fluids.